Next, let's look at a very classic question. Should we use if statements inside shaders? Earlier, someone mentioned that in the Leia Air engine, shaders can use uniform variables as conditions for branching. We conducted a similar set of tests around this topic. The first question is, can we use if statements inside shaders to avoid relying on multi-compile or shader feature, and therefore reduce the number of shader variants? The second question is, when an if statement is used, does the GPU still execute all branches behind the scenes? To answer these questions, we ran a series of tests. First, let's look at what the Unity documentation says. Unity discusses a concept called dynamic branching. Traditionally, shader branching is often implemented through static keywords such as multi-compile or shader feature, which generate separate shader variants. If we do not use those static keywords and instead write logic directly with if statements, then we are using dynamic branching. In the Unity documentation, there is a conclusion that states, when the condition of an if statement is controlled by a uniform variable, the performance impact is generally quite small. We wanted to verify this statement with actual measurements. So we created a very simple test. We wrote a shader and defined a uniform variable called _math. This uniform variable was used as the condition for an if statement. If the condition evaluated to true, the shader would execute a very expensive mathematical calculation. If the condition evaluated to false, that calculation would be skipped entirely. The variable _math was a uniform variable. The results were very interesting. When we set _math to 1, 1 is greater than 0.5, so the condition evaluates to true. In that case, the clock's value became extremely high. It reached approximately 43.5 million clocks per frame. When we set _math to 0, the condition evaluated to false. The clock's value dropped to approximately 5.9 million clocks per frame on the OPPO R17. We also created 10 different uniform conditions from 0 through 9 and tested them all. In other words, we measured 10 different false conditions. The results showed almost no difference. Even with 10 false if statements, as long as the branches were not executed, the impact on clocks was extremely small. On the Xiaomi 10, the difference was almost negligible. However, when the condition evaluated to true, the clock's value increased significantly. That makes sense because the mathematical calculation itself was very expensive. As a result, GPU workload increased dramatically. On the OPPO R17, when the condition became true, we observed a substantial increase in clocks, and the frame rate dropped sharply. Once again, the data matched the relationship we discussed earlier. The shader consumed approximately 43 million clocks per frame. The GPU's maximum frequency was approximately 430 MHz. Therefore, the device could only sustain around 10 frames per second. To isolate the cost of the if statement itself, we performed another test. This time, we commented out the expensive mathematical calculation entirely. We repeated the same test on both the OPPO R17 and the Xiaomi 10. The result was essentially identical to the previous false branch case. This tells us that simply having an if statement present does not significantly affect clocks if the expensive code inside it is not executed. From a clock's perspective, there was virtually no measurable change. So far, we have only discussed if statements controlled by uniform variables. But what happens when the condition depends on per-pixel data? To test that scenario, we replaced the uniform condition with a condition based on screen space coordinates. Specifically, we used the horizontal UV coordinate. When the parameter n equals 1, pixels on the left half of the screen have a UV x value less than 0.5, so they skip the mathematical calculation. Pixels on the right half have a UV x value greater than 0.5, so they execute the calculation. As a result, half of the screen performs the expensive operation while the other half does not. Next, we increased the parameter value. We tested n equals 10 and n equals 100. In theory, half of the pixels still execute the calculation and half still skip it. The total screen area involved remains exactly the same. However, the measured clock's values were different. Let's look at the results. When n equals 10, the screen displayed alternating vertical stripes. The white stripes represented regions where the expensive calculation was executed. We measured the clock's values for 3 scenarios, n equals 10, n equals 100, and a full-screen version where every pixel executed the calculation. When n equals 1, the screen is split into two large continuous regions. One half executes the calculation and the other half does not. When n equals 10, those regions become striped. When n equals 100, the stripes become much finer. What we observed was that the clock's values increased progressively as n increased. In other words, n equals 1, n equals 10, and n equals 100 produced steadily higher clock's values. At first glance, this seems surprising. But if we think about how GPUs execute work, it actually makes sense. As the branching pattern becomes more fragmented, neighboring pixels are more likely to take different execution paths. Inside a GPU execution unit, some threads may evaluate the condition as true, while others evaluate it as false. When that happens, the GPU often has to execute both branches. In other words, both the true path and the false path may be processed. As branching divergence increases, more pixels effectively pay the cost of the expensive calculation. This behavior is consistent with GPU execution theory. If we compare clocks and frame rate together, the trend becomes very clear. When n equals 1, the workload is approximately 24.5 million clocks per frame, and the frame rate is around 17 frames per second. As n becomes larger and the branching pattern becomes more fragmented, frame rate continues to decrease. So we can draw a few conclusions. First, when a uniform variable is used as the condition of an if statement, performance is generally not affected by branch divergence. Even with multiple conditions, the impact is extremely small. In our test with 10 uniform-based if statements, the difference was almost negligible. This makes dynamic branching particularly suitable for visual effects shaders. For example, effects often include optional features such as distortion, dissolve effects, and similar functionality. Implementing these features with if statements instead of shader keywords can have very little runtime cost. At the same time, it significantly reduces the number of shader variants. As a result, shader memory usage can often be controlled much more effectively. However, when the condition depends on non-uniform data, such as per-pixel values, the situation changes. In those cases, branch divergence can become significant and may have a noticeable performance impact.